Okay, hello everyone. We will learn about multivariate probability distributions, number 5, and this will be the end of the lecture for multivariate probability distributions. 5.9 is about the multinomial probability distribution, and the multinomial distribution is a generalization of the binomial distribution. Let's look at the definition 5.11. A multinomial experiment possesses the following properties. Number one, the experiment consists of n individual trials. The outcome of each trial falls into one of k classes of cells. So in the binomial trial, the outcome have two classes of cells. In multinomial experiment, we have k classes or cells. Number three, the probability that the outcome of a single trial falls into cell I is pi, and I is 1 to k, and remains the same from trial to trial. Notice that P1, sum of P1 to Pk is 1. So in binomial trial, P is the probability for one event, and 1 minus P is probability for the other. And if you sum P plus 1 minus P, which is 1, and in multinomial case, we have P1 for outcome I, and P2 for cell 2, P3 for cell 3, and Pk for cell k. And if we sum up all the probabilities for the cells, then it is equal to 1. And number 4, the trials are independent. And the number 5, the random variables of interest are y1 to yk, where yi equals the number of trials for which the outcome falls into cell I. Notice that yi plus y2 plus dot 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 yk equals n. Okay, so in multinomial probability distribution, the random we have k number of random variables, and since we have n identical trials, sum of y1 to yk equals to n. Okay, so this is description for the multinomial distribution. Here's definition 5.12. Assume that P1, P2, and Pk are such that sum of all Pi's are equal to 1, and each Pi's are greater than 0 for all I is 1 to k, and the random variable y1, y2, and yk are said to have a multinomial distribution with parameter n and P1 to Pk. Okay, so we say multinomial distribution n comma p1 to pk if it follows multinomial distribution, and the joint probability function for y1 to yk is given by this one, and actually it is choosing so there is cell 1, cell 2, and cell k, and the total number of items, there's n items, and among n items we are choosing y1 number for cell 1, and y2 number for cell 2, and yk number for cell k. So it is choosing n choose y1, y2, and yk, and choose y1 to yk, and this is same as this one, and factorial y1 factorial this one, and the total number of simple points, we can count it this way, and choose y1, y2, and yk. And for that simple event, the related probability is P1 to Y1, P2 to Y2, Pk to Yk. So this is why the joint probability density is given this way, where for each I and Yi equals 0, 1, 2 to n, and sum of I equals 1 to k, Yi equals n. Okay. Okay, let's move on to example 5.30. According to recent census figures, the proportions of adult persons over 18 years of age in the United States associated with 5 age categories are as given in the following table. So here's the table for here's the recent census table in United States. If these figures are accurate and 5 adults are randomly sampled, find the probability that the sample contains one person between the age of 18, one person from here, two between the age 25 and 34, and two between the age of 45 to 64. Okay, two between here, and the other are 0. So the random variable we are sampling 5. So it's actually 5 choose 1 2 0 2 0, and the probability is the first group 0.18 to 1, and 0.23 to 2, and 0.27 to second. So this is the probability. That the sample contains one person between age of 18 to 12. Yeah, this one. And actually, this is 5 factorial divided by 1 factorial, 2 factorial, 2 factorial, and 0.18 to 1, 0.23 to second, 0.27 to second. Okay, if you calculate this one, you will get the answer. Okay, let's move on to theorem 5.13. If y1, y2, and yk have a multinomial distribution with parameter n and p1, p2, and pk, then number 1, expected value of yi is equal to n times pi, and variance of yi is equal to n times pi qi. And number 2 is covariance of ys and yt is minus n times ps pt. Okay, so in multinomial distribution, the situation is like this. There's cell 1, cell 2, and cell k. And we are picking y1 number from the first cell, y2 number from second cell, yk number of from kth cell, and all the we are picking n number of items. And if the situation is like this, let's say we have ith events, yi. So here's ith cell, and we have yi number, and we can think of this situation is like this. We only focus on ith event. So here's ith cell, and the other cell, which is n minus yi event, n minus yi events. So let's consider this situation. Let's just focus on I cell. Then what we can think of this situation is that yi would follow binomial distribution. It's the situation is like whether picking the item from I cell or picking item from the other. So so each of yi can be described as like this: binomial distribution binomial distribution n and pi. Okay, so we can think of the situation like this for each of yi's, and from using the binomial distribution, we can easily show the number one. The expected value of yi is equal to n times pi, and also variance of yi is n times pi qi. And this is from the binomial distribution. Okay. And then how can we show the number two, covariance of ys and yt? And actually, these ys and yt are some of independent Bernoulli trials. So let's think about the situation again. The first cell, second cell, kth cell, and we are picking n number of items, So the simple event would be something like this. We are picking one I cell, S cell, S cell, T cell, T cell, K cell, T cell, first cell, and the number of these characters, we have n characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so if n is equal to 10, then one simple event would be this one. And here, and actually, we will construct ys or yt as sum of independent Bernoulli trials. So ys and let's define u1 to un, and ui is 1. u 1 if ith item is picked from ith cell, picked from s cell. Ith item is from okay, I will write it here. ui is 1 if ith item is from S there, S 0 otherwise, and wi is 1 or 0. 1 if ith item is from kth cell. Okay, so let's from this simple event, let's write ui. Ui is ith item is from S cell. So here, these are from S cell. So ui is u1 is 0, u1 is 0, u1 is 0, u1 is 0, u2 is 0, u3 is 0, u4 is 1, u5 is 1, u6 is 0, 0, 0, 0, 0. So this is ui's, and sum of ui's it is ys. Ys is number of items that picked from S cell. So ys can be written as sum of ui, and yt can be written as sum of wi. Okay, and for wi, for this simple event, wi is 0, 0, 0, 0, 0, t. Okay, 1, 1. So the w1 is 0, 0, 0, 0, 0, 1, 1, 0, 0, 0. This is w, and since we have two items from t cell, the sum of wi is 2, which is yt. Okay, so we can describe ys and yt this way: sum of ui and sum of wi. And then we can calculate the covariance of ys and yt, which is um, uh, sum of ui's and sum of wi's. And actually, to solve this, we can write table. So table here, u1 to un is here, w1 to wn is here. And so this is sum of all the covariance of u and w's. So this is sum of all the covariance of u, I, and w, j. And here, and from here, if I and j are not equal, if I and j are not equal, ui and wj are independent. So covariance of ui, comma wj is 0. And what about I equals j? If I and j are equal, then covariance of ui and wj is actually expected value of ui wj minus expected value of ui, expected value of wj. And from here, expected value of ui times wj. Actually, ui wj is 0. So here the ui w I when I and actually this is 0 because if one of item is picked from T cell, then it cannot be picked from S cell. So UI and WI, if one of them is 1, the other should be 0. So the expected value of UI WI should be 0. So this part is 0. Okay, let's change the color. This part is 0, and here expected value of ui, which is probability for S cell, that's PS, and EW, this is probability for T cell, PS. And so covariance of ui wi is minus PS PT. Yes, PS PT. And since we have here in the table, these diagonal parts, they are not 0, and if I and j are different, they are all 0. Covariance of u, I, and wj, if I and j are not equal, and since they are independent, they are all 0. And so we have n number of diagonal events. So we have n number of diagonal events, and covariance of UIWJ, which is minus PSPT. So it is minus n times PSPT. Okay, so this is the proof for the theorem 5.13. If you cannot understand this thing, probably read the solution for the theorem 5.13 in the textbook more carefully. Probably you would understand it. Okay, and here are homework for chapter 5.9. Okay, chapter 5.11 is about conditional expectation. Here is definition 5.13. If y1 and y2 are any two random variables, the conditional expectation of g of y1, given that y2 equals y2, is defined to be this way. If y1 and y2 are jointly continuous and defined this way, if y1 and y2 are jointly discrete. So y1 and y2 are discrete random variables. This is expected value for conditional expectation of G, and actually this makes sense because this is conditional density and this is G of y1. So this is kind of natural extension of expected value for the conditional random variable. Okay. Okay, let's move on to example 5.31. Refer to the random variable y1 and y2 of example 5.8, where the joint density function is given by this, and find the conditional expectation of the amount of cells y1 given by y2 equals 1.5. And in example 5.8, we calculated the conditional density function. We already calculated the conditional density function, and in here we want to find the conditional expectation, which is expected value of y1 given y2 equals 1.5. Okay, and here the conditional expectation is integrating dy1 the y1 times this density is 1 over y2, and actually y2 is 1.5 here, and the integration is y1 is from 0 to y2, and y2 is 1.5 here, so 1.5, and so this is the conditional expectation, and here this is y1 2 y1 squared over 2 times 1 over 1.5, and y1 is from 0 to 1.5, which is 1.5 squared 2 times 1.5, and this is 1.5 or 2, which is 0.75. Okay. Okay, let's move on to theorem 5.14. Let y1 and y2 denote random variables, then expected value of y1 is equal to expected value of y1 given y2. And actually, from here, it is important to know that the random variable here, expected value of y1 given y2 is function of random variable y2. Actually, this of g of y2. Okay, and so the outside of expectation is with respect to the random variable y2. Okay, and where on the right hand side the inside expectation is with respect to the conditional distribution of y1 given y2, and the outside expectation is with respect to the distribution of y2. Yeah, actually this is very important. So the expectation here, the inside of the first expectation, it is respect to the conditional distribution of y1 given y2, and the outside of expectation is with respect to the distribution of y2. It would be important to know that the expected value of y1 given y2, this is function of random variable y2. So it's something like g of y2. Okay, let's try to solve it. So expected value of y1, we can write it, let's consider y1 and y2 are continuous random variables, and then probably we can write it as this, y1 times f of y1, let's assume that we have joint probability density joint density function fy1 and y2, and dy1 dy2. And from here, if we have conditional density function, then we can write it as from the previous theorem, we can write it as y1 given y2 times f2 of y2 dy1 dy2. We can write it this way, and from here, this f2 y2 do not depend on y1, so we can write move this outside. So integration of integration y1 f y1 given y2 dy1 and f2 y2 dy2, and from here this one, integration of y1 times fy1 given y2, this part is actually expected value of y1 given y2 is small y2, and so we can write it as expected value of y1 given y2. Okay, let's try to solve example 5.32. A quality control plan for an assembly line involves sampling n equals 10 finished items per day and counting y, the number of defectives. So y is the number of defectives, and if p denotes the probability of observing defective, then y has a binomial distribution. Okay, so y has a binomial distribution with n and p. Assuming that a large number of items are produced by the line, but p varies from day to day and is assumed to have a uniform distribution on the interval from 0 to 1 over 4. And so actually this p is also random variable. So this is y given p. When p is given, y follows binomial distribution np, and the p it follows uniform distribution from 0 to 1 over 4. Okay, so and we want to find the expected value of y, or we want to find expected value of y, and so to calculate expected value of y, we can calculate it like expected value of y given p, and like this. So from here, the expected value of y given p, it follows binomial distribution np. So that is n times p. N is 10, so it's 10p. And from here, the p is uniform distribution from 0 to 1 over 4. So 10 times EP, and which is 10 times 1 over 8, which is 5 over 4. Okay, let's move on to theorem 5.15. Let y1 and y2 denote random variables, then variance of y1 is equal to expected value of we want to show this thing. So to show that, we want to check variance of y1 is actually expected value of y1 squared minus expected value of y squared. And from here, expected value of y1 squared is actually expected value of y1 squared given y2. And also the other part is expected value of y1 given y2, expected value of squared. Okay, and to make this as variance of this thing, variance of y1 given y2, this is actually expected value of y1 squared given y2 minus expected value of y1 given y2 squared. So to make to make this thing, we need to expected value of y1 squared given y2 minus expected value of y1 given y2 squared, and plus expected value of y1 given y2 squared minus expected value of y1 given y2 squared, and this part becomes expected value of variance of y1 given y2. Okay, and this part, this one squared, and expected value of this one squared. So the second part becomes variance of expected value of y1 given y2. Okay, so for the variance, this one squared minus expected value of this thing squared, which is the second part. So in the conclusion, this thing is expected value of the variance of y1 given y2 plus variance of expected value of y1 given y2. Okay, so this is the proof for this one. Okay, let's move on to example 5.33. Refer to example 5.32, which is the previous example. Find the variance of y. And in the previous example, y given p it follows binomial distribution and p, and also p follows uniform distribution 0, 1 over 4, and in the problem we want to find variance of y, and to calculate variance of y, since y have the conditional density, probably we can use the theorem that we just have learned. So we can use this theorem. Expected value of variance of y given p plus variance of expected value of y given p. Okay, so let's think about one by one. What about this? Expected value of variance of y given p. Here, the y given p follows binomial distribution NP. So variance of this is actually NPQ, NP 1 minus p. Okay, and this is n times EP minus n times EP squared. Okay, let's think about this later. And what about variance of EY given P? EY given P follows binomial, so EY given P is NP. Variance of NP, and this is N is constant, so N squared variance P. And here, P follows uniform distribution. So, from uniform distribution, EP is 1 over 8, and variance of P, it is 1 over 4 minus 0 squared over 12. So that's the variance of P. And actually, from the equation of this, variance of P is EP squared minus P squared. So from this equation, you can also solve EP squared. So so you can solve all the EPs, EP square, VP. You can calculate all of them from here. And so if you put these quantities, and you can solve variance of y by yourself, you can try it by yourself. I will leave it to you, and that's it. Okay. And here are homework question for chapter 5.11. And here are homework for supplementary exercises. And okay, thank you very much. And this is the end of the chapter 5, multivariate probability distributions. And see you next week. Thank you.